In this video, we're going to take a look at the negation rules in Fitch-style system. We're going to look at the negation elimination rule and the negation introduction rule. Let's get to it.
The first negation rule that we're going to take a look at is negation elimination. Let's take a look at it informally first. So a negation such as not the case P is true just in case the proposition being negated is false. And that's because not the case P just is to say is the very thing that it's asserting is P is false. Well, when is P is false right? It's right just when P actually is false. No surprise there. By the same sort of reasoning then, if we have a negated negation, so for instance, not the case P, it's going to be true just in case the negated sentence, which itself is a negation, is false. And that's because the negation at this point is saying that this negation is false. When is it right? Is right when that negation is in fact false. So what that means then is a double negation is true just in case the proposition that is being doubly negated is true. The other way to think about it is the negation symbol just tells us to flip truth values. So if we start off with P being true, and then we see that it's negated, it flips to false. But then when that's negated, it flips to true. So that's why a doubly negated proposition will be true if the proposition that's being doubly negated is true. Let's see how we represent this in the Fitch-style system. All right, so we are talking about negation elimination formally now. That is in how to apply the rule negation elimination in Fitch-style system. And by negation elimination, what we can do is move from a double negation to the proposition that's doubly negated. And the reason why we get to do that, if you'll recall, is because if we have a proposition and it's true, and the negation tells us just to flip the truth value, then our double negation has and will always have the same truth value as the proposition that's doubly negated. All right, so that's why that is a good inference. And this is the diagram that tells us how to apply negation elimination in the Fitch-style system. If somewhere in the proof we have a double negation, then we can legitimately infer the proposition that's being doubly negated. We do so by applying negation elimination, and we cite the double negation. Okay? All right, so below here we have an example of this. I specifically wanted our premise to have 3 negations. And since it has 3 negations, notice that this negation, not the case A is a cube, is being doubly negated. So it might not be obvious, but this is in fact a double negation. It's just a double negation of a negation. So by our rule, negation elimination, that's coming from our double negation in step 1, we can then infer the proposition that was being doubly negated. In that case, it's the negation. It's not the case that A is a cube. So another way to think about this is that what negation elimination allows us to do is to always remove two negations. So by applying negation elimination onto step 1, we can remove two of its negations, leaving us with it's not the case that A is a cube. All right, now let's turn our attention to negation introduction, or what is sometimes called indirect proof, or what is also sometimes called proof by contradiction. First, let's think about negation introduction informally. The part of the way that it works is that no set of true propositions can be inconsistent. And that's because by the meaning of inconsistency, a set of propositions that's inconsistent, at least one of those propositions would be false. So if we have a set of propositions, all of which are true, however many propositions there are in that set, so if we have that, and then we take another proposition, S, and we develop a new set out of it where it includes all of the former propositions all of which we know are true under our assumption. Oops. And then we add only one other proposition to that set, namely S, the one in question here. And then we find out that it entails a contradiction. Then we know that S has to be false. Now, why is that the case? Because a contradiction just lets us know that there's an inconsistency in the set that's in question. So if the set in question entails a contradiction, there's an inconsistency, meaning at least one of the propositions is false. But we already assumed that none of those were the ones that were false. So if there's any one that can be false, there's only one left, and that's S. And since S is false, by the meaning of negation, not the case S must be true. So if S is false, the negation sign tells us to just flip to the next truth value, the opposite truth value, which is true. All right, let's apply that concept now to an argument that has consistent premises. However many premises that is. Now, if you remember, when checking for validity, we get to accept all of our premises as being true. All right, we got our Fitch bar right here. Now, suppose then I introduce some proposition, and then at some point in this subproof that I've introduced, I come across a contradiction. It can't be any of these premises that cause that contradiction, because we said that they're consistent and we accepted them, for the purpose of testing for validity, we accepted them as all being true. That leaves only S as being what caused the inconsistency. And since by the word inconsistency, it means between these propositions, maybe I should use a different color, between these propositions, including the S, there's only one remaining proposition that could be false, namely S. And of course, if S is false, then if we put a negation in front of S, we flip the value then to true. So we get to validly infer then not the case S. So one way to think about what we're doing here is by us introducing a proposition for the purposes of negation, introduction, or proof by contradiction, or indirect proof. We're trying to see if we're wrong. So we introduce a new proposition and we want to see if we're wrong. We want to prove ourselves wrong. And we prove ourselves wrong if we, after making that assumption, actually come across a contradiction. All right, so let's see how negation, introduction, indirect proof, or proof by contradiction gets represented in Fitch-style. All right, so that is our diagram for the rule negation introduction. You can't see it, but up here are the premises of the argument and any of the inferences made from those premises prior to our introduction of a proposition, our assumption of a proposition. So this then, where we now have a subproof started, is us introducing a proposition. And again, what we're saying, one way to think about what we're doing here is, hey, I want to try to prove this wrong, right? I've assumed that didn't, that wasn't in the premises to begin with, nor has it already been inferred from the premises. I'm just going to put it in the proof for the purposes of seeing if I'm wrong, to see if what I'm proposing is actually false. And if after, not a good arrow, and if after introducing that assumption we come across a contradiction, then we now know that we were wrong. And since we were wrong, that means P was false, which then means that not the case P is true. So then we can end our subproof and come back out to the main proof with not the case P. So it's always not the case whatever it is that we're assuming up here. So we're always introducing the negation or adding the negation to what it is that we started off assuming, the assumption that we introduced. All right, so then we have to cite the rule, negation introduction. And what we do is we say, hey, look at the assumption that we introduced at that steps, whatever step that ends up being. And hey, notice that it eventually led to a contradiction at this step. And then that tells whoever's reading your proof why we are licensed to introduce the negation, why we can add that negation to our assumption. All right, so let's take a look at this example of negation introduction being used. One of the things that's interesting about this example is it actually doesn't have any premises whatsoever. it turns out there are things that we can prove without appealing to any premises, specifically logical truths. So what I have assumed, what I introduced into the proof, is the claim that A is a cube, and it's not the case that A is a cube. So you should be able to see that that's self-contradictory. It cannot be the case that both A is a cube and not a cube, which is what step 2 is asserting here. So I use conjunction elimination to pull out the first conjunct, A is a cube, and then again by another application of conjunction elimination, I pull out the second conjunct. It's not the case that A is a cube. And now, step 3 and 4 take the form of P and not the case P. And we said that when we have those two propositions taking that form, P and not the case P, we can use contradiction introduction, which is specifically what I'm doing here. And we're using it on 3 and on 4 to introduce a contradiction. So notice then that under the assumption A is a cube, and it's not the case that A is a cube, we arrive at a contradiction. Hence, the assumption that I introduced must be false. So notice that the inference then that we make, we end the subproof here, the inference that we make just is the inference or the proposition in step 2, except that it's being negated. And of course it's the entire proposition that has to be negated, which is why there are parentheses around the conjunction A is a cube and it's not the case that A is a cube. We do that by using the rule negation introduction. And we say, hey, why do we get to use this rule? We get to use this rule because we introduced the assumption A is a cube and it's not the case A is a cube. And then through step 2 all the way to step 5, we got to a contradiction. That licenses us then to add a negation to what it was that we introduced, because what we introduced must be false. Therefore, the negation of what we introduced must be true. Alright, so before ending this video, what we're going to do is take a look at how these negation rules operate in the Fitch computer program. The first negation rule that we're going to take a look at is negation elimination. So looking at this example that we have here, we have one premise, and it's a fairly strange premise because it says it's not the case that 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 either A is a tetrahedron, or it's not the case that it's not the case that C is large. So even though it's a strange premise, we're still going to be able to apply negation elimination to it. And negation elimination, of course, allows us to remove two of the negations. And that's because, if you'll recall, the negation symbol tells us to flip truth values. And since we only have two truth values, true and false, if I flip it twice, then I come back to the truth value that I started with. All right, we can then even apply negation elimination to the inference that we just made. And that gives us the proposition that it's not the case that A is a tetrahedron, or it's not the case that it's not the case that C is large. So the proposition in step 3 is logically equivalent to the proposition in step 1. It follows from it because of that logical equivalence. Note though, the Fitch computer program allows us a shortcut. Instead of doing those two inferences to get to the proposition that's in 3, if instead of typing out what was in the second step, I could just hit the check mark and it'll remove the largest even number of negations that are in front of the sentence that's being multiply negated. All right, so looking at 3 and 4, whichever we decide to use, you might think that by using negation elimination, you could end up with the following proposition. Right, because it looks like we could use, since there's a C as large as being doubly negated within this disjunction here, it looks like then maybe we can use negation elimination to get rid of those two negation symbols. However, you'll see that when we try to apply that rule, it doesn't work. So we can't apply the rule to double negations that are within a complex proposition. We can only use them on a proposition that's being doubly negated. One of the things that I hope that you noticed while going through this example is that complex propositions, such as 1, can be doubly negated, and the negation elimination rule can be applied to it. All right, so let's turn our attention now to see how the negation introduction rule works in the Fitch computer program. All right, so in this example, we have one premise, and the premise states that it is not the case either P or Q. So it is a disjunction that is negated. And what I want to try to prove to you is that if 1 is true, then P has to be false. That is not the case. P is true. To do that, what I'm going to do is introduce my own assumption. And I'm introducing the assumption to try to prove myself wrong. So you can imagine that at step 2, what I'm doing is, hey, let's assume that P is true and then see if that ends up being wrong. See if we can show that that is actually false. All right, so by hitting Control A, from my assumption P, I know that either P or Q is true, that the proposition P or Q is true. Why? Because if my assumption is true, if my assumption that P is true, then since that would be one of the disjuncts of either P or Q, then it's got to follow that P or Q is true. And the rule that allows us to do that is disjunction introduction. I have to cite I have to cite 2 because that's what's making 3 true, because P in 2 is my disjunct here, so that if it's true, then 3 has to be true as well. All right, let's check to see if that actually comes out correct. And it does. And now if we look at 1 and if we look at 3, we see that we have the form of P at 3 and not the case P at Q or at 1. And that's because this is the proposition P or Q, and at 1, that very same proposition P or Q is being negated. So we're saying that it's both true and that it's false. But that can't be the case. And since that can't be the case, what we can do by hitting Control A is we can introduce a contradiction. Where is that contradiction coming from? It's coming from the fact that 3 asserts a proposition to be true and 1 asserts that very same proposition to be false. So I cite 1 and 3, and that gives us our contradiction. Well, okay, so in proposition 2, I had assumed P, and I wanted to see if I could prove myself wrong. And at step 4, I did prove myself wrong because I got to a contradiction by assuming P. So since P is wrong, I know that P is false, and at step 5, that when I say not the case P, that's just another way of saying that P is false. So now I know that not the case P must be true. The rule that allows us to do that is negation introduction. And what I cite is 2 through 4. And if I just click somewhere between 2 through 4, it'll go ahead and highlight the whole thing for me. And we see that that actually follows. Let's look at one more example of negation introduction before ending this video. All right, the second example that I want to use negation introduction on is a logical truth, and it's the one that we used as an example earlier before we looked at how this works in the Fitch computer program. So we don't need any premises in this case because it's what we're going to prove is a logical truth. So what I want to show that must be false is A is a cube, and it's not the case that A is a cube. All right, so I've introduced that assumption. There's no premises, and I've introduced that because I'm thinking, hey, doesn't that have to be false? And shouldn't I be able to show that that's false? That is, shouldn't I be able to show this? That it's not the case A is a cube and not a cube. All right, in order to do that, from the assumption that I introduced in 2, I need to generate a contradiction. Well, I see that both of those conjuncts, that if they were separated from one another, would take the form of P and not the case P. And I know that I have a rule, conjunction elimination, that allows me to pull out the conjuncts of a conjunction. So I'm going to go ahead and pull out A is a cube from 2. And now I'm going to pull out not the case A is a cube from 2. And now I see that 3 and 4 takes the form of P and not the case P. So by contradiction introduction, I can introduce the contradiction symbol. Great, I've proved myself wrong. from 2, I can eventually get a contradiction showing that 2 must be false. And 6 just says that 2 is false. Alright, so the rule that allows me to do that, to, as it were, add a negation to step 2, is negation introduction. And I have to cite the subproof that leads to the contradiction. That's 2 through 5. I click anywhere between 2 through 5, and that'll cite the 2 through 5 for me. And then we'll see that the rule, if I actually write the sentence grammatically correct, we'll see that the rule checks out.
Alright, that ends this video on the negation rules in Fitch-style system. I hope it was helpful for you.